Very much for the introduction, and thanks to HitCon and all the staff and all the sponsors for letting me be here today. So I want to talk about hacking like humans, but without humans. So I think when you first see that, it's like, well, what a weird thing to say, right? Like, why do we need to hack like humans? Why can't we just hack however we want? Why does it matter what the workflow that we use is? So to answer that question, we need to take a little bit of a step back in time. So in 2016, I think as GD alluded to, DARPA hosted the Cyber Grand Challenge. So DARPA, if you're not familiar with it, it's kind of the US government organization which does things like advanced technologies like stealth planes or self-driving cars or the internet. And they wanted to answer this question, can computers hack like without having humans involved? So they set up a competition very similar to the DEF CON CTF, but 100% autonomous. So it's completely air-gapped, there's no humans involved. And the computers were tasked with finding and fixing bugs in compiled software. So all the challenges were custom written for this, and all the teams kind of used a similar approach. So a combination of things like symbolic execution, fuzzing, binary hardening. And I was on the team that won this in 2016, Team Mayhem. But one of the things that I think I took away from this is that, yes, computers can do this autonomously, right? Computers can hack and patch systems without humans, but there's a lot of caveats here. There's a lot of issues. So the first is that fuzzing and symbolic execution are really, really great techniques, but they're really exploration techniques, right? This isn't how humans go about solving these problems. If you're a human vulnerability researcher, you don't just try random inputs like a symbolic executor or a fuzzer does. You find a bug and you try to exploit that specific bug. And so these exploration strategies really struggle. If you can't really have a fuzzer generating like megabytes of files, right? That's not how it works. They only work for small files, and they just kind of explore the program and hope to get lucky. And really, this is a more fundamental issue, which is that, if you're just doing these strategies that don't really understand the code, how do you trust the results, right? Like, if you have a C program and you hook up a fuzzer to it, is your fuzzer trying SQL injection? Should it be trying SQL injection, right? I mean, maybe your C program is connected to a PostgreSQL database or something. So is your computer thinking about proper threat models when you hook it up to this autonomous system? And just in general, if you're doing something like fuzzing, when do you stop fuzzing, right? There's a lot of these things where you really need to understand what's going on in order to trust that you've done something and made something secure. So the real question is, can we still get these computer scaling benefits, but also have the benefits of humans, right? This understanding and these security properties that we get when we're hacking something like a human does. Now, luckily, there's been kind of some great technologies in more recent history dealing with these ways of thinking like humans. So maybe you've heard of something called ChatGPT. So in 2022, in November, ChatGPT was released. And this spawned a whole thing, right? Like LLMs, great. There's all these different models. And just in the past year, things about agentic coding, about reasoning models, all of these things have just been kind of inundating us. And here we are at HitCon 2025 in August, kind of in the middle of all this, with new models coming out last week and probably new models coming out next week. So DARPA decided that they would host another challenge related to the Cyber Grand Challenge, but this time we could use LLMs, right? We could use these new technologies and try to see if this might help. And part of this, I think today when we look at this, we're like, well, obviously this can help. LLMs are really powerful. But if you look back at this timeline, right, AIXCC was announced right about here in August of 2023. So this is still pretty early in this whole wave of these LLM things. So this was a pretty kind of like a guess, right? Like this might work and it might not. It's just a hypothesis that we need to test. And we can look at the whole timeline here. When things were announced, you can see it's just kind of all in the middle of this huge mess of all these models coming out every week, basically. So we don't need to talk too much about the competition. There's been some other great talks yesterday by Team Mechafish and Team Atlantis. also talking about AIXEC. So the basic idea is this time we have full code bases. So they're not custom written projects just for the competition. We have code bases of hundreds of thousands of lines or millions of lines, which are real open source software projects. And they could be written in C or Java. And once again, we need to try to figure out if we can patch this software and if we can find bugs in the software. So once again, I participated in this challenge. This is our team. This time we got third place, not as good as first, but that's okay. And I want to talk about some of the stuff that we did, partially because we spent a lot of time and resources on this. I spent the last almost 2 years of my life working on this problem. And we also spent a lot of money, mostly credits that we were given for free, thank God. But this is a really expensive area to work in. And it's nice if we can share the results so people don't have to kind of replicate everything from scratch. So to start off, if we're trying to build these systems using LLMs, well, what new tools do LLMs give us, right? Like, what can we do now that we couldn't do before? So I think people kind of get the basic idea of what LLMs are and what they do. So, all right, I'll just do this by hand. So LLMs, people talk about them being kind of like autocomplete, right? All they do is they take in a bunch of text input in the form of tokens, and then they produce more text output also in the form of tokens. And part of the thing here is that there's fundamental limitations, right? If you're doing this input to output thing, you have to have all of the data that is created in the output based solely on the input or on the training data. So a good example of why this matters is if we do something like, let's say we wanted to ask an LLM what the weather is today in Taipei, right? Well, the LLM has absolutely no idea what the weather is today, right? All it can do is tell me, wow, you really should just get a smartphone and read your weather app, which is helpful, but that's not what I wanted to know. So this is still a really powerful building block, but there's obviously limitations here. But the next obvious thing that we can do is we can hook this up into something called an agent. So everyone talks about agents and agentic coding, and it's really just a simple idea, which is just you throw a loop around this text completion, and now you can do additional things, right? So if the agent wants additional data, it can request it using something like tool calls, where we say, hey, I'm going to get additional data and use it. So if we take the same example as before, okay, what's the weather in Taipei? But this time we insert some additional data into our prompt saying, hey, LLM, you have a tool which allows you to get the current weather. Then the LLM is going to say, great. Now I can solve this problem, so I'm going to check the weather in Taipei using the tool that you provided. So we have to concatenate all these messages together, right? We have to add them all up so that we can keep extending them one at a time. So we get the message that we first started with, the next message that the LLM gave us, and now we run our tool on this get weather thing that it requested, right? So maybe we say 35. So the nice thing is that the LLM is pretty smart, right? 35 is not a very complete answer to this question, but the LLM is smart enough to use a little bit of intuition here, so it can say, great, 35, you probably meant Celsius. We can convert that into Fahrenheit for you as well. Yeah, so the nice thing is that these agents can be a lot more powerful, right? They can keep working on these problems until they come up with something useful. Obviously, we have to pay a cost for that. So in particular, these end up being something like 100 times more expensive in practice. So if we think of like a single text completion being something like 1 cent, then an agent is going to be something like $1. These are just kind of order of magnitude estimates that are useful for when we're thinking about these problems. So the next piece in our toolbox that we're going to use is an LLM-based classifier. So classifiers are very common in machine learning or anything like this. Very simple concept, right? We have a multiple choice question, and we want to know the answer. So a common example that people use is like this hot dog, not hot dog app, if you've ever heard of this. So the idea is, you take a picture of something, and you're like, is this a hot dog or is it not a hot dog? Very simple idea. So we see this, great. On the left, we have a hot dog. On the right, we have a shoe. Shoe is not a hot dog. Easy problem. But there is a problem here when you start using this very naively, which is that there's no real scores for confidence, right? So what do you do if you have something in between a hot dog and not a hot dog, right? If I show you this picture, Well, this is a little bit more ambiguous, right? It's not a hot dog, but it's not a shoe either. And you really want to have a little bit of nuance in your responses here. The nice thing is that this is actually pretty easy to do with LLMs. So LLMs don't just output words, they actually output probability distributions of words. And so what we can do is we can use the probability distribution directly. And so instead of getting a binary output of like 0 or 1, yes or no, we can get a whole spectrum of answers. And now we can say something like 60% yes, 40% no. And this is much more powerful and useful than just saying some binary result. So this is it, right? I mean, there is plenty of other cool things that people can and have built with LLMs, embeddings, other things, but these are the only building blocks that we're going to talk about. And so how can we use this to actually build something interesting? So again, the whole point of this project is we want to get patches, and we want to get inputs which trigger bugs, and we want to use these magical new LLM things to do it. So for patching, really, I don't think we need to spend much time talking about patching. I think people kind of get the idea. It's 2025. You've all heard of Claude Code or Codex or whatever. So yeah, that works, right? Like you can basically just give one of these LLM agents some access to source code, and it can do a good job. At least when there's a human in the loop, we get how this works. So our agent specifically, this is kind of the rough outline of how it's set up. So these are the tools that we give it. So we have 3 classes of tools. We have tools for reading code, tools for making changes, and tools for testing the changes that it's made. So for reading code specifically, like we don't use something like Bash. We have very specific things that are based on kind of more fundamental static analysis tools. So the LLM can read a definition, it can find references, and then for applying patches, we use something like a unified diff format with some kind of fuzzy logic. For testing patches, obviously the LLM might wish to test a patch that it creates, but we can also automatically test this, right? We don't have to wait for it to say like, I totally tested it and it's good. We don't have to trust that. We can verify this deterministically by running it every time it completes. The other kind of interesting thing that we do is we also add sub-agents here. So you might want to have a very simple question where you need to read the definition of something, but you also might have a more complicated question. And for a more complicated question, we can use a sub-agent, which still has the same access to tools, but is tasked slightly differently with trying to answer these higher level queries about the source code. So that's a little bit abstract, so we'll follow a quick example. So this is a lot of text. You're not going to read the text, I get it. I'll send you a link later on, and you can actually view all of these if you want to at home. But the basic idea is we're going to prompt all of this deterministically by our code, right? We have some sort of template, and that's how we're going to fill it out because there's no human involved to type in a little chat window. So this will tell it about the bug that we're interested in, and the model's going to say, great, I see that there's something here. I want to read a definition, right? I need to read the definition for the code that you said had the bug so I can understand what the problem is. And now we can run that, right? We can use normal static analysis and code browsing tools to find the definition it requested, and then we can send that along. And the LLM can read that and try to patch the vulnerability. But it doesn't always work, right? So here's an example where it tried to patch it, and then it runs a test, and the test fails. And that's OK, because it's in a loop, right? An agent is just this text completion inside of a big loop. So it can keep running. The patch is bad, so it calls undo, right? Very human, sort of normal thing to do. And now it says, well, I don't understand what went wrong, so I need to ask a very high-level question. I need to understand what was going on, so I will ask this sub-agent that I had access to, right? I can't just read the code to understand exactly what went wrong. I'm going to ask a bigger question about what's the purpose of some specific variable or something. So it does that, and now it can try a better patch. So, OK, whatever. Patching stuff, we get it. Again, 2025, agentic coding, not that exciting. So we have a patching agent. We can make patches. All we have to do is feed in the data from somewhere, right? But where do we get the data from? We don't have humans involved. Luckily, this brings us to the part that I find much more exciting, which is the offense side of things. So again, I think that it's important to follow the human workflow because I think the human. So We're doing offense. We want to try to follow a human workflow, right? So obviously, all human vulnerability researchers and penetration testers work a little bit differently. But I think that there's kind of a vague pipeline that people follow, right? The first idea is we're going to come up with ideas for bugs, right? Maybe we do this by reading code. Maybe we do this by getting really drunk. Maybe we do this by going to bed and waking up with wonderful ideas in our head. But we come up with some set of ideas. And then we need to actually investigate them, right? A lot of these ideas are not going to pan out. And then if the ideas look plausible, then we're going to spend a little bit more time trying to actually exploit them. So maybe we can use LLMs to do the same sort of thing, right? We've got 3 different parts here, right? Can LLMs find these bugs? Can they evaluate if we come up with bugs? And can they actually generate the POCs if we have really strong candidates for something that could be a bug? So for generating bug reports, well, okay, first off, obviously we have static analysis, right? Computers can run static analysis tools. We get it SemGrep or CodeQL. We use Infer from Facebook in our system. It's not very exciting, but it totally works. If we want to use LLMs, we can sprinkle a little bit of LLMs on top by maybe annotating the bug reports that it generates with a little bit of extra information. If we have a code diff, it's also not too hard, right? A code diff is pretty small. Maybe it's a few hundred lines of code. We can just throw that in an LLM agent. We decided an agent is like $1 or something to run. That's not so bad, right? Even if we have like 100 different diffs, we can spend $100. That's a small number of dollars. But what if we have a repository with like 1 million lines of code and we don't have diffs and we want to find bugs, right? This is a much harder problem if we want to use LLMs. And again, I think it's important to try to use these tools as much as we can because they're new and they're exciting, and we really want to understand what the limitations of these tools can be. So the first thing is right away we realize that if we have millions of lines of code, we can no longer use agents on the entire code base. That's just too much data for these things to work well. So we have to use these single shot completions, right? We can't wrap it in a loop because the loop is going to blow up our costs. So basically what we have to do is we have to just go and look at the code and just ask if there are bugs. And this kind of works, but there's a lot of issues, right? So we can do this a couple ways. We can break it down by functions. We can say, is there a bug in this function? We can give it a bunch of files and say, like, can you find bugs in any of these files? But there's a lot of really nuanced things here. And realistically, this could be its own talk, right? Just trying to figure out how to do static analysis with LLMs. I think it's a really deep topic, and there's a lot of interesting things. But the basic idea is you have to be very precise, right? You can't just ask if there are bugs, because what is a bug, right? Is a documentation error a bug? If there's like a typo in the code, is that a bug, right? An LLM is really tuned to safety and doesn't like saying that things are safe. So you can't just ask if there are bugs. You need to ask very precise questions. So very precise questions help the LLM to not hallucinate, right? If you ask a vague thing, then you're going to get a vague response where it kind of stretches to fill the available space of the ambiguity that you used. Part of this is also we can ask for a lot more detail. And similar to some of the early techniques that we saw in the LLM field, like chain of thought, asking the LLM to explain not just is there a bug, but like under what conditions does this bug manifest? How can I reach it? Specifically what type of bug? You know, if we do all these much more specific things, we see that the performance of this system improves drastically. So basically, you know, again, there's a lot of details here. Our code is open source, so you can read it. But it totally works. We can use a bunch of different LLMs from different providers, which all maybe have different failure modes and different things that they recognize. And it finds real bugs, not just AIXCC, like whatever injected bugs. So we found real 0 days in real projects with this. But it's also not magic, right? We still have false positives like any static analysis tool. So when we try to hook this up to our pipeline, well, we get our bug reports, we feed that into our patching agent. Our patching agent costs dollars. We run static analysis, which has lots of false positives. If you do the very simple math here, you see that this is going to cost a lot of money real fast. So we need to work on that step 2 of that human pipeline, which is evaluating the bug reports that we're getting and deciding if they're useful. So how do humans look at these reports, right? And again, I think there's a number of different ways that humans do this, right? Everyone's a little bit different. But in general, if you're given 10,000 reports and you're told to look at them and figure out what's going on, then there's not a lot that you can do, right? You have to look at these as quickly as you can and try to sort out junk reports from non-junk reports. Let's see if this, yeah, it's coming, okay. So humans are gonna quickly look at all these reports. Maybe they write a regex, maybe they just ignore everything that says null dereference because they don't care about null dereference, but they've developed some sort of quick heuristic that they can use to develop, to sort through these quickly. And then if you have anything left after you're doing this really quick triage, then you can do something more careful. So let's do a very similar pipeline for LLMs. So the quickest thing that we can do is start off by using that LLM classifier that we talked about before. Right? So if we get a bug description, why don't we just ask the LLM, like, is this a false positive, yes or no? This sounds really nice in practice. There's some obvious issues, right? If I give it a piece of source code like this, and someone says, hey, this destination buffer, there's an overflow in it if you call this nginx decode base64 function. And all I have is the access to this source code. And I look at it and okay, well, how do I decide if this is real or not? I see that the source buffer comes from a cookie, right? Cookie is obviously untrusted. I can use my intuition to tell that cookie is potentially attacker controlled. So that's evidence in favor of this being exploitable. But then I see that the destination is actually not just a simple like character array. It's a typed variable that has a length field. And so if it has a length, well, then maybe this is safe because I'm not going to write past the end of this length. But then it turns out, if you keep reading this deeper, nginx decode base64 just completely ignores that length field and will just copy arbitrary amounts of data. And how are you ever going to know that if all you were given was this single function, right? It's an impossible task. So part of this is you have to rely on the intuition, but there's also things that we can do to make this easier for scoring and easier for this triage process. So the first part is we can annotate information. So if we run these static analysis reports or we use LLMs to generate these reports, we can add additional information about what functions are related and kind of what invariants they're expecting or how they're expecting things to work. The other thing is that it turns out that if you provide a lot more detail, so something like falsifiable information, that's a lot easier to score. If I say specifically, hey, there's a buffer overflow, it occurs on line 256 when this variable is copied into this variable, it's very easy to look at that and say like, no, you misunderstood this. But if I just say there's a buffer overflow in this 250 line function, now I have to look through every single line to try to understand what's going on. So if you're very specific, then the performance of these classifiers works a lot better. And there's a lot of other issues here. Once again, this is a very deep topic that could be its own talk, but we get the kind of basic idea. So in practice, this kind of works, at least on some projects. Not every single project is perfect, but we can do something like 95% of the actual bugs end up in the top 10% of the scores from this classifier, which is kind of amazing when that works. But this still isn't perfect, right? So if we're running the static analysis pipeline, we get whatever, 10,000 results with a bunch of false. So we're trying to triage these reports. We have a lot of false positives. And we have this tool, which is kind of nice, right? It can do this classification task, and the classification task is very cheap, right? It's single shot LLM completions. So we can run this, but even if we're filtering out, if we're getting 10% of the results, 10% of the results is still 1,000 reports, right? 1,000 reports is still going to be a lot of false positives. Alternatively, we can use agents, right? Agents are nice because they get to browse code, so they don't have the same problem we had before where there wasn't enough context to actually answer these questions. So naively, there's kind of a couple options, right? We can take the really cheap approach and we get 1,000 false positives, or we can take the really expensive approach and get 0 false positives and spend $100,000, right? Neither of those seems like a good idea. Luckily, there's no reason we have to do this all at once, right? We can do this iteratively. So what we can do is we can start off taking this really simple, cheap, fast approach, and that's going to give us something like 1,000 reports with most of the bugs contained in it. If we have 1,000 reports, now we can spend a little bit more money to do the next iteration of this, right? So now we can look at this first level agent, which costs something like 50 cents, and now we only spend $500 instead of $5,000 triaging these reports. This is going to get us more results, right? It's still not perfect, so there's still false positives, so it's something like 50 results in general. But now we can do the same thing, right? We spend $10 on each of those results, and now we can keep doing this iteratively. So this gives us maybe something like $1,000 of spending to get results very close to that $100,000 of spending, because we're doing this iteratively, one step at a time, kind of refining it as it goes along. So this is a lot more scalable, and yeah, we're going to miss some of the true positives, right? This isn't a perfect pipeline. But if we are worried about that, we can tweak some of these numbers, right? We can adjust what's going on so that we're getting kind of the results that match our budget and our security and our risk profiles. All right, so what does this look like, right? So we get bug reports. We feed those into a filter. We can patch them. Now we get a bunch of patches. Wonderful. So the problem is we also want to generate inputs, right? We want to know if these bugs are real, and well, what do we do, right? Do we do fuzzing? I like fuzzing, but you could also tell that I kind of have a little bit of a love-hate relationship. So really what I want to do is use LLMs. How do we use LLMs for this task? So let's talk about generating the POCs with LLMs. So the first problem is that LLMs don't generate binary output, right? This isn't that complicated of a problem, but they generate natural language, and the actual POCs are not going to be natural language. So we have to pick an input format that is natural language, so we pick Python, right? LLMs absolutely love Python. That's basically their native language. And it also has a lot of advantages. So first, if we want to do something like output 10 kilobytes of data, if we're using Python, we can just like use a really simple thing here, right? We just say like, whatever, the byte times 1024, and that's going to output 10 kilobytes of data, and we don't have to pay for each token. It also allows us to do things like calculate checksums, calculate lengths, all that. So this is not really a problem. We're using Python, it's wonderful. The next issue, though, is that if we're doing this, we need to be speaking through fuzzing harnesses, right? So anytime you get one of these projects, you need to be giving it binary input, right? We're not standing up a web server. We're trying to fuzz a web server, or at least provide input to a web server that's very easy to test. So one problem is that there can be a lot of different fuzzing harnesses available, right? If you're talking about something like curl, the curl project talks to a different number of formats, something like 30 different formats and protocols. So there's like 30 different fuzzing harnesses available, and your LLM is going to need to choose which of those it wants to target. The other problem is that just harnesses are kind of confusing, right? If you give an LLM something like Nginx, the LLM is really smart. The LLM says, Nginx is a web server. I'm talking in Python. I'm going to import the requests module, and I'm going to talk to localhost, and I'm going to send it some HTTP requests. And that's not what we want, right? We're talking over binary files doing fuzzing. So if we try to deal with all these things at the same time, what we start seeing is that everything just suffers, right? The LLM is very distracted. It's splitting its attention between trying to figure out which harness to use, how to do this encoding problem, and how to deal with exploitation all at the same time. So agents really want one task. If you can give it one task that it can focus on, they're going to do a good job. Even once you split that up into two, they just toggle back and forth, really making no progress on either one. So the easy way to do this, or at least one easy way to do this, is to break down the problem, right? Well, first, let's say, don't worry about bugs, don't worry about POCs or vulnerabilities. We're just going to produce an input encoder. So we're going to have a dedicated agent, which is going to produce something like a Python input encoder and export this as a library. So just as a quick example, here's some source code from the curl project. And this is what the fuzzing harness looks like for curl. And if you look at this, it's kind of not clear what's really going on, right? It's taking this type length value data, it's unpacking it, there's a bunch of kind of weird binary stuff involved. So trying to understand what's going on is a bit annoying. But if we give this to an LLM and ask it to develop an input encoding library for it, it creates something like this, right? This is much more simple, right? We get 4 parameters, they're all strings, and it's not just strings, but they're very clear strings, right? I know what a URL is, I know what a username is. So we can do this, and we can even provide documentation because LLMs are great at generating prose. The nice thing about this is we can also test it, right? We can say, hey, you told me that there's supposed to be a username here. What I'm going to do is I'm going to set a GDB breakpoint or something. I'm going to make sure that the username string I provide actually makes it into the program. So we've provided this intermediate step that we can test and we can validate before we pass it on to the next stage. Now, the next problem is just kind of a lot more fundamental, which is that producing POCs is just really hard work, right? If you do this like as a vulnerability researcher, there's so much code you have to read through. Maybe a vulnerability is like 15 call levels deep in the code. How are you going to actually make the LLM understand all of the context that's necessary? And even if you're doing this with a language model that has like this ridiculously large context window, right? Some of these language models at least claim that they have something like a 2 million token context window. But in practice, that's not actually true, right? Like, you can feed that much data into them, and it won't give you like a request error when you try to ask it. But the practical usable token limit is something like 32,000 tokens. So if you start trying to give it too much data, you start getting more hallucinations, they get stuck in weird loops, and just lower intelligence for whatever you want to say intelligence is on an LLM. So there's a couple ways that people have dealt with this in practice. So the first one is using context compression. So basically, you can ask LLMs to just compress, summarize the message history into something smaller. The other possible way of doing this is to use subagents. So subagents are really nice. Basically, the idea here, we talked about it before with that kind of source questions agent, is if you ask kind of a vague question, right? If I say like, how big is this argument when I call this function? What's the maximum size of it? Trying to answer that question, you might have to read a lot of different pieces of code, right? You might need to read through some macros. You might need to read through 6 levels of call stack to understand what conditions are placed. But the actual response here is going to be relatively small, right? If it's like 1,024 bytes, then the response is just going to be the maximum size is 1,024 bytes. That's like 10 tokens total. So it's kind of naturally compressing the output. So when we run our POC producer, we do the same thing. We use these subagents, specifically the source code questions and a debugging questions, and we use those as subagents where the interface is natural language. They can spawn off and do a whole bunch of work inside of these subagents, and then they return a really simple result. Notably, we do not have tools that directly read source code inside our POC producer, which is kind of a weird choice. But it hides a lot of distractions, right? If you're reading through all the source code necessary to understand a POC, and you hit something like a to-do, right? If there's a to-do in the code, maybe your LLM agent is like, is that something I'm supposed to do? Right? It might get a little bit confused. So let's follow another example of this. So here, again, I get it. You can't read all that code. We're just going to talk through it at a high level. If you want to look afterwards, you can. So this is from the FreeRDP project. So we inject some code, a little bit of backstory about what it is, FreeRDP. We give it information. You have a bunch of different harnesses. You need to choose which of these harnesses is correct. And here's the bug that we're trying to exploit. In this case, it is a signed integer overflow in some random function inside of FreeRDP. So the first thing is that it's going to call the subagent, right? It doesn't have the ability to read source code directly, so it has to ask the subagent to explain to it a little bit about what the vulnerability is, why this is interesting, and all that. And the next thing is it can ask, which harness should it use, right? We talked before that this was actually a pretty complicated problem, but the answer is going to be a really simple string, right? It's going to say, like, you should use harness number 4. And so we can hide all of the complicatedness inside of a subagent and just return a really simple result. We can get the input encoder. Then we can start kind of actually working on this, right? We ask about the actual structure for the protocol. Well, once again, we see some issues. LLMs are not perfect. Subagent failed. But that's OK. We can start rephrasing the question, and the thing can start working on trying to write some inputs. So it runs this, asks some questions to the debugger. The debugger is very helpful, right? It doesn't just say, yes, you hit the code that you wanted. It'll say, yes, you hit the code that you wanted, but you didn't actually do all the parsing that you were expecting to do. So this keeps running, get a deeper POC. get more complicated structures that are things that I don't really know about because I don't know this protocol, but the LLM seems to understand what's going on. So we can run this for a while. So in this particular case, the agent ran for like 40 minutes. It made like 16 calls to these different sub-agents, but only cost about $4, which is pretty nice. And in the end, we see the stack trace, right? It triggered the exact bug that we were trying to trigger. And we can look at what's going on. So here's the actual code that it produced. The comments are things that the LLM added nicely to its POC code. And we can look at the hex dump for it. This is not a trivial bug. It's actually interesting. So first off, this wasn't an injected bug from the competition. This was actually a 0-day and free RDP. And fuzzing, in our case, had never even hit this function. Didn't trigger the bug, but it never even hit the function at all if we look at the coverage data, even if we used upstream data from OSS fuzz to initialize what we were working on. And the bug was found, it was triaged, and it was triggered completely autonomously using LLMs, no fuzzing at all. So this is kind of mind-blowing to me that this worked, and I think this is really exciting. So great, we have something, it works. LLMs can follow human workflows, right? I don't know that it's perfect, but they can kind of do it. And as we get these better models, this whole system is just going to magically get better because the models are going to be smarter. So I'm very low on time, but I'm going to go through a couple tips because that was all very high-level talk, and I'd like to leave you with some useful information if you try to do these things yourself. So the first is minimize the amount of work that you ask an agent to do. So if you ask an agent to do something that you know it has to do 100% of the time, well, you should have just done that work for the agent yourself. Right? So if I need to ask the agent, like, you're supposed to develop a harness input encoder for this specific harness function, I can read that harness function myself, and I can just give that whole code. I don't need to let the agent go and kind of find that stuff. If you're using these tools, you need to think really hard about what tools you're using. Right? You can't just give every single tool imaginable to an LLM and expect it to do a good job. One of the examples I like here is if you think about this like a video game, maybe a text adventure, but maybe something like Portal. If you're playing the game of Portal, right, you need to be given a portal gun, right? Obviously. How are you going to play the game without a portal gun that explains how you're doing this, right? It tells you that you're going to shoot portals, you're going to jump through them. You get the weird little jumpy boots things, you're going to jump on top of blocks or whatever. But if someone gave you extra tools, right, if someone gave you lockpicks in the game of Portal, this is just going to confuse you. Right? Like, what am I going to do with lockpicks? Every time I get to a new level, I'm going to think that I'm supposed to pick a lock on a door, and I'm just going to be super confused about what's going on. So you really need to think about tools, and you shouldn't just give general tools that can do everything imaginable. There's also, you should run lots of evaluations. I think people get the basic idea here. Overall, there's a lot of nuances with how we do this, and I think the only way to understand how these things are going to work for your specific problems is to do evaluations in your specific use cases. So I can't tell you things are going to be good or bad, or which agents or which LLM providers are going to suit your workflow. You need to do those evaluations yourself. So just in conclusion, I think LLMs are solving real problems, right? They can do things somewhat like humans are doing it. I don't think people are using these to their full potential. I don't think that what we built is a perfect system. I think that the whole limiting factor here is just the tools that we're building for these systems are not yet there. I think if we took the LLMs from last year and we built better tools for them, they could keep getting better for years to come. And we didn't have to talk about math, right? This is a black box, right? We don't have to talk about tensors or transformers or matrix multiplications. So I think you should all go out and try to build something with this, and I think you'll find it's easier than you expect. So yeah, that's it. If you scan this QR code, we have things like source code, those agent traces that I was showing you. We have a little way of viewing them. We have blog posts, all of that. I don't think I have much time for questions, but I will be around the conference. If you find me and want to ask me stuff, just do so. So thank you.
Wow, thank you so much. And sorry for the hardware issue. And I think this is a great talk showing. I should be speaking in Chinese. So 非常谢谢这个 Tyler 带来我们这个超级精彩的演讲。我们这3个队伍的比赛其实有一点不同样方式，就是里面听到跟昨天又不太一样技巧这样子。那我们因为有一点超时，我们开放一个问题好不好？有没有谁要问问题 ？Alan， 你是不是举手举很久了 ？So still one question from Alan.
Yeah, I asked this yesterday to Shellfish, but I would like to ask again to the DEFCON CTF champion. Did you use this tool in the DEFCON CTF competition and in the traditional rules game rule? How did it work best for you?
Yeah, so we actually did kind of a couple days before DEF CON CTF, we ported some of our tools to work with decompiler output. So we run either Ghidra or Binary Ninja and feed those results into the same source code-based system. It's not as nice, right? There's a little bit of a difference between a decompiler source code and like annotated human written source code, but we were able to find bugs. I think it had a similar false positive rate, about 50% or something at the end of a pipeline, because it wasn't going to generate all the inputs itself, because we didn't have fuzzing harnesses. But we were able to use it. We did use it in the CTF. It did help us write bugs. I think we probably still would have won without it, but it was nice to have.
好，那我们再次用热烈的掌声，谢谢泰勒带来这场精彩的演讲。Thank you.